My name is Vezeteu Eugeniu, and this is my master thesis project on Camera-Lidar calibration for autonomous driving, realized in a partnership with Aalto University School of Electrical Engineering and Finnish Geospatial Research Institute under the National Land Survey of Finland. All experiments were performed on the hybrid Ford Mondeo autonomous car, embedded with lidars, cameras, radars and GNSS sensors. The goal is to realize mono and stereo camera calibration, synchronize the sensors, propose an automatic points collection technique, perform Camera-Lidar extrinsic calibration and develop an occlusion handling algorithm. Camera calibration was realized with OpenCV and 2 calibration boards for data collection. 2 datasets were collected, with cameras inside and outside the car, to estimate the windshield effect on calibration. The windshield introduces noises that increase the focal length mostly in the y direction and shifts the principal point, down on the x-y axis. It also increases the reprojection error. It has been shown that complete distortion model can deal with the introduced noise, even if not completely, it can decrease the windshield effect. Stereo images were rectified using rotation and translation between cameras. The 3D point cloud was generated based on disparity map. In the following video, you can see an example of unsynchronized sensors. Synchronization is an important phase, that ensures that sensors provide measurements of the same scene at the same time. In this work, GPS clock was used to align camera and lidar sensors. Ransack plane fitting was applied to filter the calibration board points from the original point cloud. Standard fitting methods may suffer due to point cloud sparsity. We propose to use the convex hull on board's margins. We fit a template and extract the board's corners from the lidar point cloud and pixel correspondences from camera frames. In the extrinsic calibration pipeline, feature extraction is applied to the lidar and camera data. The calibration is done either by using 2D 3D, or 3D 3D points correspondences. The estimated transformation was applied to convert lidar points to camera frame and project them on the image. The lidar sensor is used as a mainframe and cameras are plotted relative to it. In Camera-Lidar fusion, each lidar point gets the color from the camera frame, however, this causes some ambiguities, due to sensors occlusion. The occlusion problem is caused by the fact that sensors have different locations. For example, some of the blue points from the image are seen by lidar but not by camera, therefore the color of the occluded points will be wrong. Our idea is to filter the occluded points in the camera space. We sort the projected points by depth. For each point we compute k nearest neighbor and treat a point as a box. We enforce the closest points in the image frame to have the same depth. In the example you can see the projected point cloud on the image before and after occlusion removal algorithm. We have a comparison between camera and lidar 3D scene reconstruction. We notice that camera disparity-based reconstruction is dense and noisy while lidar-based reconstruction is accurate but sparse. In the final scenario we present the camera and lidar synchronization, fusion and occlusion removal results. Thank you for your attention.